The night sky was a problem for Heinrich Olbers in 1823. He was a German astronomer, a good one, and he asked a simple question. If the universe goes on forever and it's full of stars, why is the sky dark at night? It should be blazing white. Every line of sight should eventually end on a star. The whole sky should be as bright as the surface of the sun, but it's not. It's mostly black. This question became known as Olbers' paradox. The answer took more than a century to figure out. It involves the universe having a finite age, about 13.8 billion years, and the fact that it's expanding. The light from the most distant stars hasn't had time to reach us. And the light that does reach us is stretched out, redshifted by the expansion of space itself. The simple observation that the sky is dark at night tells us that the universe is not static and eternal. It had a beginning, it is changing. This was a profound shift in thinking. It opened the door to modern cosmology. It also opened the door to other, more unsettling questions. If the universe had a beginning and is changing, how will it end? And is the very fabric of the universe, the vacuum of space itself, truly stable? Or is it just waiting for a reason to collapse? We have found that the laws of physics, the very constants that hold our reality together, seem to be balanced on a knife's edge. This balance suggests our universe might not be in its final, most stable state. It might be in a temporary state, a false vacuum, and if that's true, it could, without any warning, transition to the true vacuum. This event is called vacuum decay. It would not be an explosion you could see from a distance. It would be a bubble of new physics expanding at the speed of light, rewriting reality as it goes. You would not see it coming, you would not feel it. One instant you are here, the next you, the Earth, the sun, the galaxy are gone, replaced by a region of space with different rules that do not support the existence of matter as we know it. The dark night sky told us the universe is not what it seems. The study of subatomic particles is telling us something far more alarming. It's telling us our existence might be an accident of cosmic physics, a temporary state of being that could end at any moment. Number 17, the Higgs boson's mass is precariously light. The Large Hadron Collider confirmed the Higgs boson's existence on July 4th, 2012. Its discovery filled the final gap in the standard model of particle physics, but it also gave us a number. A very specific number. The mass of the Higgs boson is about 125 giga-electron volts, or GeV. For a subatomic particle, this is heavy. It's about 133 times more massive than a proton. But for the stability of the universe, it's terrifyingly light. The stability of the vacuum, the very ground state of our universe, depends on the interplay between two key particles, the Higgs boson and the top quark. The top quark is the heaviest known elementary particle, weighing in at about 173 GeV. The Higgs boson gives other particles mass through the Higgs field. The top quark, being so heavy, interacts very strongly with the Higgs field. These two forces are in a cosmic tug-of-war. The Higgs boson tries to stabilize the vacuum. The top quark, through its powerful interaction, tries to destabilize it. The final outcome depends on their masses. Physicists can plot the stability of the universe on a chart, with the Higgs mass on one axis and the top quark mass on the other. This chart is divided into three regions. One region is for a completely stable universe. In this scenario, our vacuum is the one true vacuum, the lowest possible energy state. It can't decay into anything else, it's here forever. Another region is for an unstable universe. In this scenario, the universe should have collapsed from a vacuum decay event almost instantly after the Big Bang. We would not be here to discuss it. The third region is the sliver in between. It's the region of metastability. In this state, our universe is not in the true lowest energy vacuum. It's in a false vacuum, a temporary state. It's like a ball resting in a small dip on the side of a large hill. It's stable for now, but a sufficient jolt could push it over the edge and it would roll down to the bottom of the valley, the true vacuum. When physicists plotted the measured masses of the Higgs boson and the top quark, the point landed squarely in the region of metastability. Not deep inside the stable zone, not in the impossible unstable zone, right on the edge. This is perhaps the most direct piece of evidence we have. The foundational model of our reality, the standard model, which has been tested and proven correct to incredible precision, is telling us that our universe is living on borrowed time. The number 125 GeV is not just a property of a particle, it's a parameter that describes the fundamental nature of our reality. And that parameter points towards an existence that is temporary. It's a universe that could, in principle, cease to exist. Number 16, the top quark is just a little too heavy. The top quark was discovered at Fermilab's Tevatron accelerator in 1995. Its discovery was a triumph, but its properties continue to be a source of cosmic anxiety. As mentioned, the stability of the Higgs field, and thus the universe, depends on the masses of the Higgs and the top quark. The top quark's mass of around 173 GeV is what pushes the calculation towards instability. If the top quark were just a little lighter, say by a few percent, the point on the stability chart would shift firmly into the stable region. Our universe would be secure. We could all rest easy knowing that the vacuum of space is the true final ground state. But it isn't lighter. It is stubbornly, precisely heavy enough to place us in this precarious metastable state. The precision of this measurement is critical. Particle physicists at the LHC and other colliders are working tirelessly to nail down the top quark's mass with ever greater accuracy. Each new measurement refines our understanding of where we sit on that stability chart. So far, every improvement in precision has kept us within the metastable region. The error bars are shrinking, but our cosmic predicament remains. This isn't just an abstract calculation. The top quark's strong interaction with the Higgs field has a physical meaning. It contributes a large negative energy to the Higgs potential. The Higgs' own contribution is positive. At low energies where we live, the positive term wins and our vacuum is stable. But the calculation shows that at extremely high energy scales, far beyond what we can create on Earth, the top quark's negative contribution could overwhelm the Higgs' positive one. This would cause the Higgs field's potential energy to turn over and plunge downwards into a much deeper, more stable state. That's the true vacuum. The fact that one particle, the top quark, has a mass that so perfectly balances the universe on this knife edge is a profound sign. It's a hint from the universe itself. The laws of nature did not have to be this way. The top quark could have been lighter. The Higgs could have been heavier. The fact that they are what they are, leading to this specific unsettling conclusion, suggests that the possibility of vacuum decay isn't just a wild fantasy. It's a direct consequence of the measured properties of our world. Number 15, the concept of a false vacuum is not speculation. The idea of a false vacuum isn't just a theoretical gimmick invented to scare people. It's a core concept in modern physics, particularly in quantum field theory and cosmology. It arises naturally from our understanding of how fields and energy work. A vacuum, to a physicist, isn't empty space. It's the lowest possible energy state of a system, the ground state. A quantum field, like the Higgs field, permeates all of space. The value of this field determines the properties of the vacuum. In a simple system, there is only one ground state, one true vacuum. But in more complex systems, you can have what are called local minima. Think of a landscape with many valleys. The deepest valley is the true vacuum, the global minimum energy state, but there might be other, smaller valleys at higher elevations. These are local minima. A ball placed in one of these higher valleys will stay there. It's stable for a while. This is a false vacuum. Our current understanding of the Higgs field suggests it has this kind of potential energy landscape with multiple valleys. We are living in one of the higher, shallower valleys. The standard model predicts that there is another, much deeper valley available. This is the true vacuum. The energy difference between our false vacuum and the true vacuum is immense. The transition would release this energy. The laws of physics as we know them are tied to the specific value of the Higgs field in our valley. If the field were to tunnel into the deeper valley, its value would change. This change would cascade through everything. The masses of the W and Z bosons would change, the masses of quarks and electrons would change. The fundamental interactions that govern chemistry and nuclear physics would be altered. Atoms could not form, stars could not ignite, the complex structures we see in the universe would be impossible. The existence of multiple energy states for fields is a standard feature of physics. It's not the weird part. The weird part is the mounting evidence that we happen to be living in one of the temporary ones. Number 14, quantum tunneling is a real, observed phenomenon. The mechanism that allows the universe to transition from a false vacuum to a true vacuum is quantum tunneling. This sounds like science fiction, but it's a fundamental and well-verified aspect of quantum mechanics. It happens all the time, just on a much smaller scale. On the quantum level, particles don't behave like solid balls. They have wave-like properties. This means there is a non-zero probability that a particle can pass through a barrier it shouldn't be able to cross according to classical physics. It's like a ball spontaneously appearing on the other side of a solid wall. The probability is tiny for large objects, which is why we never see a person walk through a wall. But for subatomic particles, it's a common occurrence. Quantum tunneling is the reason the sun shines. Inside the sun's core, protons need to get extremely close to fuse together. Their positive electric charges create a powerful repulsive barrier. According to classical physics, they don't have enough energy to overcome this barrier. But thanks to quantum tunneling, there's a small chance they can just tunnel through it and fuse, releasing the energy that powers our solar system. The transistors in every computer and smartphone also rely on quantum tunneling to function. The flow of electrons is controlled by tiny barriers that can be tunneled through under the right conditions. So the process for our universe's destruction is not a hypothetical one. It's a real physical mechanism that is essential to the functioning of the universe as we currently know it. In the case of vacuum decay, it's not a particle tunneling through a barrier in space. It's the Higgs field itself tunneling through a potential energy barrier. A random quantum fluctuation somewhere in the universe could, at any moment, provide enough localized energy to push a tiny patch of the Higgs field over the hill and into the true vacuum state. The probability of this happening in any given cubic meter of space in any given second is astronomically small. But the universe is astronomically large and has been around for a very long time. Once that tiny bubble of true vacuum forms, it's a one-way trip. The bubble is in a lower energy state, so it's stable. It would begin to expand outwards in all directions at the speed of light. The fact that the universe relies on quantum tunneling for its creation of starlight, while also being threatened by the very same mechanism on a cosmic scale, is a deep and unsettling irony of physics. Number 13, we live in a universe primed by cosmic inflation. The theory of cosmic inflation is our best explanation for several key features of the universe, like its flatness and the uniformity of the cosmic microwave background radiation. Inflation proposes that in the first fraction of a second after the Big Bang, the universe underwent a period of mind-bogglingly rapid exponential expansion. It was driven by a quantum field called the inflaton field. The important part for our discussion is how inflation ended. The universe was in a high-energy, false vacuum state driven by the inflaton field. Then, this field decayed, settling into a lower energy state. This transition released a tremendous amount of energy, which, created all the matter and radiation we see today. This process is called reheating. In other words, our universe was born from a vacuum decay event. A transition from one vacuum state to another is not just a theoretical possibility for the future, it's the leading theory for our own past. The universe has done this before. The vacuum state that drove inflation was a false vacuum. Its collapse created our universe. The Standard Model suggests that the vacuum state that we currently inhabit is also a false vacuum. This historical precedent is a powerful sign. It establishes that the universe is capable of existing in multiple vacuum states and transitioning between them. The end of inflation was a graceful exit. It created a universe suitable for the formation of galaxies, stars, and life. The next vacuum decay event, the one from our current Higgs field state, would not be so graceful. It would be a transition to a state that is likely hostile to any form of complexity. The fact that our universe was born from a process so similar to the one that could destroy it is a sobering thought. It suggests that such transitions are a natural, perhaps even common, part of cosmic evolution. We are just living in one of the intermediate stages. Number 12, the landscape of string theory suggests we lost a lottery. The standard model of particle physics is incredibly successful, but it's not a complete theory. It doesn't include gravity, for example. One of the leading candidates for a theory of everything is string theory. String theory proposes that fundamental particles are not points, but tiny vibrating strings. One of the consequences of string theory is what's known as the string theory landscape. The theory doesn't predict one single unique universe. Instead, it predicts a vast number of possible universes, perhaps 10 to the power of 500 or even more. Each of these possible universes corresponds to a different vacuum state with different physical laws, different particle masses, and different fundamental constants. This collection of all possible vacua is the landscape. It's a multi-dimensional version of the hilly landscape we used to describe the Higgs potential. There are countless valleys, each representing a possible universe. Some of these valleys might be stable. Many would be false vacuums. If this landscape picture is correct, then it's highly improbable that our universe just happened to land in the one true lowest energy vacuum state out of such an immense number of possibilities. It's far more likely that we are just in one of the many, many metastable false vacuum states. It would be like tossing a ball into a massive mountain range with trillions of valleys and having it land perfectly in the single deepest one, Death Valley. It's possible, but statistically it's much more likely to end up in one of the countless other higher altitude valleys. The string theory landscape provides a theoretical motivation for why our universe might be metastable. It frames our existence not as a given, but as the result of a cosmic lottery. We happened to emerge in a vacuum state that was stable enough for long enough, and with the right physical laws for intelligent life to evolve. But the theory also implies that there are other, deeper valleys out there. It suggests that our current state is not special or final. It's just one stop on a potentially vast cosmic map of possibilities, and a transition to a different, more stable stop is always a possibility. Number 11, the accelerating expansion of the universe is a puzzle. In 1998, two separate teams of astronomers made a shocking discovery. They were using distant supernovae to measure the expansion rate of the universe, expecting to see it slowing down due to gravity. Instead, they found the opposite. The expansion of the universe is accelerating. Something is pushing space apart. This mysterious something was given the name dark energy. Your dark energy now appears to be the dominant component of the universe, making up about 70% of its total energy density. Our best explanation for dark energy is that it's a property of the vacuum itself. It's the coast of having space. This is also known as the cosmological constant. Here's the connection to vacuum decay. The energy of our current false vacuum state is what we measure as dark energy. It has a small positive value, which is why the universe's expansion is accelerating. The true vacuum, the one our universe could decay into, would have a different energy density. According to the calculations, the energy of the true vacuum would be a large negative value. A universe in that state would not just stop accelerating its expansion, it would immediately collapse in on itself in a big crunch. The bubble of true vacuum expanding at the speed of light would be a wall of space-time collapsing new physics. Everything inside the bubble would be instantly crushed out of existence. The existence of dark energy is a sign that the vacuum is not empty, it has a non-zero energy. The smallness of this energy is one of the biggest mysteries in physics, but its existence confirms that the vacuum is an active, energetic component of the cosmos. The theory of vacuum decay then simply states that this energy level is not the lowest possible one. The accelerating expansion we observe every day is powered by the very same false vacuum energy that makes our universe vulnerable to collapse. It is a constant, universe-wide reminder of the potential energy that could be released in a catastrophic phase transition. Number 10, we would have no warning whatsoever. The most terrifying aspect of a vacuum decay event is its absolute stealth. The trigger is a random quantum fluctuation. It could happen anywhere in the universe at any time. It could happen in the room with you right now, or it could happen in a galaxy a billion light years away. Once the bubble of true vacuum forms, it expands in all directions at the speed of light. Nothing in the universe can travel faster than the speed of light. That is the ultimate speed limit for any information. This means there is no way to get a warning. You cannot see the bubble coming. No telescope could detect it. No signal could outrun it. If the event happened in the Andromeda Galaxy 2.5 million light years away, we would have 2.5 million years before it reached us. But we wouldn't know it. We would continue to observe Andromeda as it was 2.5 million years ago. By the time the light from the event's beginning reached us, the bubble wall itself would arrive at the exact same instant. The information of our doom and the doom itself travel at the same speed. The transition is instantaneous. One moment, the atoms in your body are governed by the familiar laws of the Standard Model. The next moment, the bubble wall passes through you. The Higgs field snaps to its new true vacuum value. The masses of your electrons and quarks instantly change. The forces that hold your atoms together are no longer the same. Your constituent parts would fly apart or be reconfigured into some new, exotic form of matter dictated by the new physics. You would not experience this. There is no you to experience it. Your consciousness, your thoughts, your very physical form would cease to exist in a time frame smaller than it takes for a nerve impulse to travel from your finger to your brain. This is not like an asteroid, which we can see coming, or a supernova, which we can observe from a safe distance. This is a fundamental change in the rules of reality itself. Its arrival is perfectly synchronized with the first possible moment we could ever know about it. This inherent undetectability makes it a unique kind of cosmic threat. It's a pure probability, a roll of the cosmic dice, with no precursor and no escape. Number 9, high-energy collisions could, in theory, be a trigger. When the Large Hadron Collider was about to be turned on, there was a small but vocal group of people worried it could create a microscopic black hole that would swallow the Earth. Physicists produced detailed safety reports showing this was not a risk. But another, more subtle concern was also raised. Could the high-energy collisions at the LHC trigger a vacuum decay event? The idea is that smashing protons together at nearly the speed of light could create a tiny fleeting concentration of energy high enough to kick a local patch of the Higgs field over the potential energy barrier, creating a bubble of true vacuum that would then consume the universe. This is a legitimate question to ask. If the universe is in a metastable state, is it wise to be creating the highest energy collisions on Earth? Scientists at CERN took this very seriously. They studied the problem extensively. Their conclusion, laid out in the 2008 LHC Safety Assessment Group report, was that it is safe. Their reasoning is based on nature itself. The universe is constantly bombarding the Earth with cosmic rays. These are particles, mostly protons, accelerated to incredible speeds by supernovae and other violent cosmic events. The most energetic cosmic rays ever detected have energies millions of times greater than what the LHC can produce. These high-energy cosmic rays have been striking the Earth, the Moon, the Sun, and other astronomical bodies for billions of years. We have not observed any of these collisions triggering a vacuum decay. The universe has been running this experiment for us at far higher energies for eons. If it were possible for such a collision to trigger the decay, it almost certainly would have happened by now. While this is reassuring, the fact that physicists had to seriously consider and study this possibility is itself a sign. It treats vacuum decay not as a fantasy, but as a real physical process that must be accounted for when we push the boundaries of high-energy physics. The question, cooled our experiment destroy the universe, is not one that scientists in most other fields ever have to ask. The fact that particle physicists do, and that they have a plausible physical mechanism for how it might happen, underscores how close to the fundamental workings of reality they are operating. Number 8. The lifetime calculation has immense uncertainty. So, the universe appears to be metastable. The next logical question is, how long do we have? Physicists have tried to calculate the expected lifetime of our false vacuum. The calculation is incredibly sensitive to the precise values of the Higgs and top quark masses. It also involves some very complex quantum field theory. The number they come up with is enormous. The estimates often range from 10 to the power of 100 years to numbers even more fantastically large. To put that in perspective, the current age of the universe is a mere 10 to the power of 10 years. So, on the one hand, this is good news. The universe is likely to survive for a time so long that the human mind can't really grasp it. But there are two huge caveats here. First, the calculation comes with massive error bars. The uncertainty in the top quark's mass alone can change the calculated lifetime by many orders of magnitude. A tiny tweak in that measurement could bring the lifetime down dramatically. As we refine our measurements, we get a clearer picture, but for now, the number is fuzzy. Second, and more importantly, this is a probabilistic calculation. It's like radioactive decay. If you have a single atom of a radioactive element, you know its half-life, but you can't predict when that specific atom will decay. It could decay in the next second, or it could last for many half-lives. The lifetime of the universe is the same. It's a statistical average. The calculation does not say the universe will last for 10 to the power of 100 years. It says that the probability of it decaying in any given year is incredibly small. But that probability is not zero. A non-zero probability means it can happen. It could happen now. The event is not forbidden by any law of physics. The fact that it is statistically unlikely to happen in our lifetime is comforting, but it is not a guarantee of safety. The universe does not care about our comfort. The calculation itself, while yielding a large number, confirms that the decay is a possibility. The very act of being able to compute a lifetime for the universe implies that it has a finite one. Number 7. The anthropic principle offers a tense explanation. Why do the fundamental constants of our universe seem so perfectly tuned for the existence of life? If the strength of the electromagnetic force were slightly different, atoms couldn't form. If the strong nuclear force were slightly weaker, stars couldn't ignite. This is the fine-tuning problem. One controversial but compelling answer is the anthropic principle. It states that we observe the universe to be the way it is, because if it were different, we wouldn't be here to observe it. This can be combined with the idea of a multiverse like the one suggested by the string theory landscape. If there are countless universes, each with different physical laws, it's not surprising that we find ourselves in one of the rare ones that is hospitable to life. The rest are sterile and unobserved. How does this connect to vacuum decay? The anthropic principle can be used to explain why we live in a metastable universe. Perhaps truly stable universes, the ones in the deepest energy valleys, have physical laws that are hostile to life. Maybe their vacuum energy is so negative that they collapse instantly. Maybe their particle masses don't allow for complex chemistry. So the only universes that can produce observers like us are the ones in these temporary metastable false vacuum states. Our existence, then, is tied to the very precarity of our universe. We live here because it's on a knife edge. This turns the problem on its head. The metastability of our vacuum isn't a terrifying flaw, it's a necessary precondition for our own consciousness. We have selected by our very existence a universe that is capable of ending catastrophically. This is not a comforting thought. It suggests that our cosmic home is a temporary shelter, a lucky pocket of stability in a much larger, more hostile reality. It implies that the threat of vacuum decay is not an accident, but a feature of any universe that could ever wonder about its own existence. The price of consciousness might be the knowledge that the stage on which it plays out is fundamentally irredeemably fragile. Number 6, new physics could make things worse. The Standard Model is not complete. We know this. It doesn't include gravity, it doesn't explain dark matter or dark energy properly. There must be new physics beyond the Standard Model. We just don't know what it is yet. This is where things get even more uncertain. All the calculations about the stability of the vacuum are based on the Standard Model. They assume that the model's equations hold true all the way up to the highest energy scales. This is a huge extrapolation. It's very likely that new particles and new forces will appear at higher energies. These new discoveries could change the stability calculation completely. They could make things better. A new particle could interact with the Higgs field in a way that stabilizes the vacuum. If we discovered such a particle at the LHC, we could all breathe a sigh of relief. The threat of vacuum decay would recede, but they could also make things much, much worse. A new particle could destabilize the vacuum. It could lower the height of the energy barrier separating us from the true vacuum, making it easier for a quantum fluctuation to push us over. It could shorten the calculated lifetime of the universe by many orders of magnitude. We could be much closer to the edge than the Standard Model currently suggests. The problem is, we don't know. The existence of unknown physics beyond the Standard Model adds a giant question mark to the whole discussion. It means our current assessment of the risk is based on incomplete information. It's like trying to predict the stability of a building when you only have the blueprints for the first few floors. There could be a fatal flaw in the foundation that you can't see yet. This uncertainty is a sign in itself. Our most fundamental theory of reality is telling us we are in a precarious state. And at the same time, we know that this theory is not the final word. The final word could bring salvation, or it could confirm our worst fears. Number 5, the graceful exit. Problem in inflation is unsolved. Let's go back to cosmic inflation. The theory states the early universe was in a false vacuum that decayed, creating our universe. This process needed to happen in a very specific way. The decay couldn't happen too quickly, or the universe wouldn't have had time to expand and flatten out. But it couldn't happen too slowly, or inflation would go on forever, creating an empty universe. The transition had to be just right. This is known as the graceful exit problem. Many models of inflation struggle to achieve this. It's hard to get the inflaton field to roll down its potential energy hill slowly and then gracefully settle into the new vacuum state, releasing its energy to create matter. While there are models that work, the problem highlights a deep sensitivity in the physics of vacuum decay. The dynamics of these phase transitions are complex and not fully understood. This relates to our current situation. The calculations for the decay of our current Higgs vacuum are based on simplified assumptions. They assume a smooth, straightforward tunneling event. But the lessons from inflation suggest the process could be more complicated. Could the transition get stuck? Could it create weird intermediate states? We don't know. The fact that our own cosmic origins are tied up in a vacuum decay event that is itself difficult to model and understand should give us pause. It shows that these events are a fundamental part of cosmology, but they are also on the cutting edge of our theoretical understanding. The unresolved questions about the universe's first vacuum decay are a shadow hanging over our predictions about its last one. It is a reminder that we are dealing with physics of an almost unimaginable scale and complexity, and our current tools might not be sharp enough to see the full picture. Number 4, the laws of physics might not be universal. We assume that the laws of physics are the same everywhere. An electron in the Andromeda galaxy has the same charge as an electron on Earth. This is a foundational assumption of cosmology, but what if it's not entirely true? The string theory landscape suggests the possibility of different domains, or pocket universes, each with its own vacuum state and its own laws of physics. Our observable universe would just be one such pocket. If this is the case, it's possible that the boundaries between these domains are not static. Our universe could be colliding with another bubble universe that has a lower vacuum energy state. Such a collision would look identical to a spontaneously generated vacuum decay event from our perspective. A wall of new physics would sweep through our universe at the speed of light. Some cosmological models even propose that our universe was formed from such a collision. This idea changes the nature of the threat. Instead of a random internal quantum fluctuation, the trigger could be external. It would mean our fate is not just in the hands of quantum probability, but is also tied to the dynamics of a larger multiverse we cannot see. We could be a stable island in a calm sea, or we could be on a collision course with another, more stable continent. There is no way to know. The possibility that the laws of physics are not universal, but are instead local byproducts of a particular vacuum state, opens the door to the idea that our laws can be replaced. This is the very definition of a vacuum decay event. The simple act of questioning the universality of physical law is, in essence, questioning the permanence of our own reality. Number 3, the search for supersymmetry has found nothing. For decades, one of the most popular ideas for physics beyond the standard model was supersymmetry, or SUSY. Supersymmetry proposes that every known particle has a heavier superpartner. This idea is mathematically elegant and solves several problems in the standard model. One of the problems it helps with is, the stability of the Higgs vacuum. In many supersymmetric models, the contributions of the new superpartner particles act to stabilize the Higgs potential. They push the universe firmly into the absolutely stable category. For years, physicists were confident that the Large Hadron Collider would start discovering these superpartners. It was a major goal of the LHC program, but it hasn't happened. Despite years of searching at ever higher energies, there has been no sign of supersymmetry. Not a single superpartner has been found. This is a major puzzle in particle physics. It's often called the nightmare scenario for the LHC. The absence of evidence is not evidence of absence, but it has forced physicists to consider that supersymmetry, at least in its simplest forms, might be wrong. This has direct implications for vacuum stability. One of our best hopes for a natural mechanism to guarantee a stable universe has failed to materialize. Its absence leaves the standard model's prediction of metastability standing. We are left with the bleak picture painted by the particles we have found, without the convenient rescue that was promised by the particles we hoped to find. The persistent failure to find evidence for these stabilizing theories is a sign by omission. The universe is looking more and more like the simple, unadorned, and metastable place described by the standard model. Number 2, black holes do not seem to trigger decay. Microscopic black holes might be able to trigger vacuum decay. The extreme gravity and energy density at the center of a black hole could, in theory, be enough to catalyze the transition to the true vacuum. The universe is filled with black holes, from small, stellar mass ones to the supermassive giants at the centers of galaxies. If they were efficient triggers for vacuum decay, the universe should have ended long ago. The fact that it hasn't is a good sign. It places strong constraints on the physics of the decay. It means the energy barrier must be robust enough to withstand the conditions inside a typical black hole. However, this observation is not a get-out-of-jail-free card. Stephen Hawking showed that black holes are not truly black. They evaporate over very long timescales by emitting Hawking radiation. As a black hole evaporates, it gets smaller and hotter. In its final moments, it would release a burst of very high-energy particles. It has been theorized that this final burst from an evaporating primordial black hole could be energetic enough to trigger the decay. Primordial black holes are hypothetical black holes that might have formed in the early universe. We haven't definitively observed any yet, so while existing, large black holes seem to be safe. The universe might still be populated by these tiny evaporating time bombs. The fact that the universe is still here tells us that if primordial black holes exist, their final evaporation burst is not a guaranteed trigger. But it doesn't rule it out completely. It's another area where our incomplete knowledge forces us to live with uncertainty. The apparent safety of black holes is a constraint, but a loose one. It helps us model the properties of the false vacuum, but it doesn't eliminate the threat. Number 1, our existence is the most fragile state of matter. Look at the universe. Most of it is empty space, a near-perfect vacuum. The rest is mostly hot plasma in stars or diffuse gas clouds. A tiny fraction is bound up in planets, asteroids, and dust. And on one of those planets, an even tinier fraction has organized itself into complex structures capable of thinking. Life, and particularly intelligent life, is an anomaly. It requires an incredibly narrow range of conditions. It relies on the subtle and complex rules of chemistry. Chemistry, in turn, relies on the fact that the masses of the electron, proton, and neutron, and the strengths of the fundamental forces are exactly what they are. A vacuum decay event would not just change these values slightly. It would rewrite them completely. The new state of the universe inside the bubble of true vacuum would be a profoundly different place. Would atoms exist? Probably not as we know them. Would the forces support any kind of complex structure? It's highly unlikely. The energy released from the phase transition itself would create a hot, dense plasma of whatever new particles exist in the true vacuum. The true vacuum state is, by its nature, a simpler, lower energy state. It's a state of cosmic retirement. Our universe, with its complexity, its stars, its life, is a high-energy, elaborate, and temporary configuration. It is fragile. The ultimate sign that a vacuum decay could erase our universe is the simple fact that our universe, as we know it, is the kind of thing that can be erased. It is not the ground state, it is an excited state. All excited states in physics eventually seek to decay to their ground state. An atom in an excited state will emit a photon to return to a lower energy level. Our entire universe may be no different. Its existence is a temporary deviation from a simpler, more stable reality. The fact that we are here to observe this fragility is the most profound and unsettling sign of all. We are the complex patterns that can only exist because the universe has not yet settled into its final, boring, and lifeless equilibrium.